All right, team, welcome back from Thanksgiving holiday. I hope everyone had an enjoyable holiday and did not do any statistics because that would be painful. Unfortunately, you have to do some more. So that's the bad news. There's more to learn, and admittedly, this is some of the trickiest stuff that you'll see all semester. Potentially, depends on how well I teach it, I suppose. But the good news is that really we only have 2 more weeks left of lecture. And if I do my job, then we should end up completing all of the lecture material this week. And next week will simply be a review for the final exam. There will be homework and a quiz assigned for this week covering chapter 10. So there will be one more quiz and probably some review material to earn a few more points before the final exam. So there you go. So let's jump right in. In 10.1, we started talking about some of the terminology and basic conceptual framework for hypothesis testing. And that's all good and well. I suppose it was kind of confusing because you didn't have any context. We were just throwing a bunch of vocabulary at you and some ideas, and you didn't know exactly how it was useful. So now we're going to actually use it. In this section, section 10.2, we're going to be conducting what we call hypothesis tests for population proportions. Okay, so everything that we learned back in chapter 9.1, I believe, we started talking about the sample proportion distribution. I think that was 9.1, somewhere in there. We covered the sample proportion distribution and all the stuff that we could do with that. Now we're going to put it to work. Okay. So you're just going to have to bear with me. The best way to learn how to do a hypothesis test is just to do a hypothesis test. So I'm going to try to give you a framework in which to structure your solutions so that this doesn't feel quite so daunting. So let's dive right in. Okay, so in this example, there's a polling firm that asks 1,000 voters if they are in favor of a certain policy, whatever that policy might be. 534 of those voters responded yes. Great. The firm wants to know if the majority of voters are in favor of the policy based on the sample, right? So this is inferential statistics, which means we want to use sample data to draw conclusions about the population. This firm has collected sample data and is now interested in whether or not the results of this sample data are statistically significant enough to suggest that more than half of the voters prefer this policy. Okay, so let's see how we can use hypothesis testing to determine whether or not that's a good assumption to make or not. Okay, so the way this is going to work is you're going to read the problem, and the first thing you're going to do to solve it is you're going to identify the null hypothesis and the alternative hypothesis. Now, the null hypothesis is the easy one. It's the one that always contains some sense of equality. Okay, it's the status quo. So the firm wants to know if a majority of voters are in favor of the policy. So the null hypothesis, which is the hypothesis that everything is stays the same, so to speak, there is no exception, then we would expect that half are in favor or half or not, or maybe less than half. So for us, the P value here for the null hypothesis will be less than or equal to 0.5. Now we know this is the null hypothesis because it has equality. Okay. Sometimes, and in your book in particular, instead of writing less than or equals to, they just write equals to, because it really, I suppose, doesn't matter. But this is, I think, the more correct way to do it. So the null hypothesis is that half of the people are in favor and are not, or maybe less than half. Okay, because what the alternative hypothesis is that more than half, a majority, that is, more than half are in favor of the policy. Okay. Now, reading this sometimes can be a tricky thing to identify. What are the hypotheses? But this is a necessary first step to solving one of these hypothesis test problems. Identify the null hypothesis, identify the alternative hypothesis. Now, that's not all that she wrote. There's one more thing we have to do here, and that is identify which of these two hypotheses the researchers are interested in verifying. Okay, so if in reading the problem, there will be some indication of which of those two are the one that the researchers are interested in. And here we see that the firm wants to know if the majority of voters are in favor of the policy. So that's the hypothesis that the firm is interested in. So which of the two hypotheses is that? That's the alternative hypothesis. So this one is the claim. The claim could be either of the two hypotheses, but it can only be one of them. And there will be some context clue as to which one is the claim. Which one is that are the researchers claiming or wanting to be true? So the researchers want there to be a majority in favor of this policy because they're, say, being hired by a politician who's wanting to campaign on this particular policy, but needs to know whether or not that's a good strategy based on the constituents. Okay. Identify the hypotheses, identify the claim. First steps. The next step for the population proportion problems is to identify whether or not our sample distribution is approximately normal. So for the sample proportion distribution, we know that there are two main criteria to ascertain whether or not the sample is approximately normally distributed. And that is that NP times 1 minus P is greater than or equal to 10, and N, little n, is about 5% of big N, the population size. Okay. So of these two, the first one is probably the most important. Generally speaking, the second one is confirmed by the fact that the populations are so large anyways, that any sample is probably going to be less than 5%. So, who is the population here? It's the American vote, all the registered voters in America. So that's a huge number, and 1,000 is definitely less than 5% of the total voting population in America. So this one you get usually for free without much need to worry about. The first one, however, you do need to pay attention to. This is a condition on basically on the variance of the standard deviation for your distribution. So let's see what this would be. We have 1,000 for our N, and then 0.5 for P, and then 1 is 0.5 for 1 minus P. So that's going to equal 250, which is definitely greater than 10. So now we know that the sample distribution is approximately normal. That's absolutely essential in order to conduct the hypothesis test. If we don't have normality, then things get complicated. Okay, so we've identified the hypotheses, we've identified which of those two hypotheses is the claim, and now we've verified that the sampling distribution is approximately normal. So now what do we do? Okay. To conduct the test, what we need to know what it is we're actually testing for. What is the issue? So this is what is going on. We have a distribution for the population that we are assuming. Okay. So we assume the null hypothesis is that essentially the null hypothesis is assuming that the distribution for the population is normal and that its mean is 0.5. What we are testing is whether or not this assumption is valid. So is the null hypothesis valid or not? In other words, is the population distribution normal with a mean 0.5 or not? Well, what we do is we assume that it is, and then compare the sample data to the population assumption and see whether or not this would be a rare occurrence with respect to that population distribution, or whether this would be a common occurrence. So this particular sample is one of many samples that we can draw from this population. We crunch the numbers and compare the values that we get for the sample to the parameters of the population. And if this assumption is valid, then more likely than not, the statistics that we compute for our sample should relatively match up well with the distribution of the population. But if this particular sample ends up being extreme, then that could suggest that this hypothesis is wrong. So in other words, we assume that the population is normally distributed with mean 0.5. We then look at the sample and compute its mean. So we compute p hat, essentially, which we know is x over n. And we see where does that p hat land within the distribution. So for us, that is 534 out of 1,000, which is 0.534. So that's somewhere over here, 0.534. The question is, how far over is it? Is it within the main body of the distribution, or is it in the tail, somewhere over here? This, whether or not 5.534 falls within the green part or the red part, is going to depend on the spread of the normal distribution for the population. So we need to compare this value to this value, essentially, for the same distribution, and see whether or not this is relatively close to this value or if it's off in one of the tails. So how do we do that? Well, in order to compare these two separate things, the population to the sample, we need to convert them both into z distributions. Once we do that z transform, then we can compare them together and see whether or not this 0.534 is actually relatively close to 0.5 or if it's relatively far away from 0.5. So how do we do that? Well, there's a slight complication here, which is we need to know where this cutoff is. Okay, so this cutoff is going to depend on how much type 1 error we allow into our test, which means, in other words, that it depends upon the alpha value that we've seen over and over again as we've been working on with these distributions. So what is the alpha value? Well, the alpha value is actually determined by the researchers. The researchers set their alpha value according to how much type 1 error they want to permit into their study. So you have a control there, right? But remember from last lecture, the more if you make the alpha value really small so that you make the allowable limit of type 1 error really small, then you inadvertently but unavoidably increase the amount of type 2 error that you permit. So the alpha value is arbitrary, but there are some common alpha values that are usually selected, and one of them is 0.05. So the alpha value is going to tell you where this cutoff point is, and we'll see that in a second. Okay, so how do we actually conduct the test? To conduct the test, we are going to first figure out what the z value is for this 0.534. Ran out of room. So what is the z value for that 0.534? Well, remember that in order to do that transform, you take the p hat minus the p and then divide by the sigma p hat, right? So that's the how you get that test statistic or the z transform. Okay, so you have to identify all of these values. Yep. And you need to know how to compute sigma p, right? So remember that sigma p is equal to p times 1 minus p over n square rooted. Okay, so we need to do that z transform. So this is essentially the z of the 0.534. We're figuring out what this would be in z land. So that's 0.534 for the p hat minus 0.5 all over the square root of 0.5 times 1 minus 0.5 over 1,000. So punch that in. 0.534 minus 0.5 divided by parentheses square root 0.5 times 0.5 because 1 minus 0.5 is 0.5, and then divided by 1,000. Close parentheses. And I did something wrong. Yes, I did. Need to make sure that the numerator is in parentheses as well. Oops. There we go. 2.15. Okay. So that is the Z value, the Z transform for 0.534. Right. So we're seeing essentially, again, you need to think about the distribution. And what we're seeing is that in a standard normal world where the mean is 0 and the standard deviation is 1, the value 0.534 is 2.15. Okay. Now what we want to know is that in the green area or the red area, right? Remember the picture on this side, I said, you know, if the 0.534 falls in the red area, then it's bad news bears. If it falls in the green area, it's good news. By the way, I didn't really make this clear, but red area and green area, the idea is coming from these greater than or equal to's and these strictly greater than, right? So because the alternative hypothesis is strictly greater than, that means that we're just, the only rejection area that we have is on the right. It's pointing to the right and it's only on one side. And this is why we call this a right-tailed test. So the red area, which we call the rejection region, is going to be on the right. And we know that because this is a greater than, strictly greater than, so it's pointing to the right. And that's going where that red area begins depends on the alpha value, which is the amount of type 1 error that we allow. And if it's not stated, then we assume 0.05. Otherwise, they'll state what the alpha value is. So now we need to see, where does 2.15 fall? Is it in the red area or the green area? In order to ascertain that, we need to find the cutoff point for the red area, which we call Z alpha. Well, Z alpha we can get by using the inverse norm function. And all we have to do to find the value is take 1 minus alpha. So for us, alpha is 0.05. So we're going to take the inverse norm of 1 minus 0.05. So that's going to give us the cutoff point. One minus 0.05 in the inverse norm function, and we get a cutoff at 1.64. So Z.05 is going to be 1.64. Okay, so we compute the cutoff value, we compute the Z transform for the test statistic, and now we see that the cutoff point is 1.64, which is going to be somewhere like right here. So what do we find? We find that the Z transform for 0.534 was 2.15, fell within the red area. We call the red area the rejection region. So if this value, falls within that rejection region, then we reject the null hypothesis. Okay, so we now know that if we were doing this not in Z land, but back in P land, that the 0.534 would actually fall somewhere over here in the red area. Okay, so that tells us that we need to reject the null hypothesis. Okay, so once we can reject the null hypothesis, then we can come to a conclusion. How do we come to a conclusion? we use that awesome flow chart I showed you in the last lecture. So let me say this before we move on to the conclusion, just to make it clear. What was the result of the test? We got that Z of 0.534 was greater than Z of 0.05, or no, I shouldn't say, yeah, that's fine. Z alpha. So this implies the result of the test is that we reject the null hypothesis. H naught. So that's the result of the test. So what's the conclusion? So this is why I introduced the flow chart. How do we come to our conclusion? Okay, so flowing from the chart, we say, does the claim contain equality? Which is to say, is the claim, are we claiming the null hypothesis or are we claiming the alternate hypothesis? We are claiming the alternate hypothesis. So we go this route, we go down the no. So we claim H1, then we ask, do we reject the null hypothesis? The answer was yes after we did our test. So what is the conclusion? Sorry. And this is why I show you the chart, because it can be hard to word the conclusion. So once we go the yes route, the actual conclusion is the sample data supports the claim that blah, 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 blah. What was the claim? So the conclusion is the sample data supports the claim that essentially P is greater than 0.5. Okay, so that is what we are working towards. So that was a long, complicated situation. Let me try to restate it so that it makes more sense. So here's a big reprisal. We read the problem, we identify the hypotheses. Once we identify the hypotheses, we also identify the claim. Which of the two hypotheses is the claim? All that comes from reading the problem. Once we've identified the hypotheses in the claim, we know whether we have a right-tailed test or left-tailed test or a two-tailed test. Since the alternative hypothesis was a strictly greater than, we know this is a right-tailed test. Great. Our next step was to verify or confirm that the sample distribution is approximately normal. So we do that using these two criteria. Once we know the sample distribution is approximately normal, then we can compare the sample distribution to the population distribution, the proposed population distribution, with a test. So in the test, we, according to the alpha value and the hypotheses, we determine what the rejection region is and what the failed to reject region is. So since there's a greater than, we know the rejection region's on the right, and the alpha value will tell us where the cutoff point is for that rejection region. Where does it start? Our main aim is to figure out whether the sample proportion is far away or close to the proposed population proportion. The way we do that is we take both the population values, we take the population and the sample, and we transform them both into z's so we can compare them clearly. So what does that mean? That means we take whatever the p-hat value is from the sample, and we convert it into its z value by using this formula. And once we have that value, we compare that value to the z alpha value, which is determined by the alpha value that's set by the researchers, which is generally 0.05, but it could be something different. So we compute the z alpha value and then compare it to the z value for 0.534 for our sample proportion. If the sample proportion z value is greater than that particular cutoff point, then we know it falls within the rejection region, which tells us that the result of the test is to reject the null hypothesis. Once we know that we can reject the null hypothesis, we then can form a conclusion. How do we form the conclusion? We use this flow chart, which helps us formulate our conclusion. So the result of the flow chart depends on whether the claim was H0 or H1, and whether we rejected or failed to reject the null hypothesis. We have 4 different conclusions we can come to. So that is the flow. That's how a hypothesis test works. I know it's a lot, and honestly, you think this is a lot. The book goes over 2 other ways to conduct these tests, and it gets pretty complicated. So I'm just going to teach you one way to conduct these tests. It'll always work. But if you don't like it for whatever reason, then you can try to wrap your head around one of the other approaches. They're all interchangeable, but I just assume not confuse you and just teach you one straightforward approach. Okay, so let's do another example so you can see how this plays out. Okay, in this example, we're told that 24% of Americans say raising a girl is easier than raising a boy. And this was based on some national survey. A separate survey was conducted, and it found that out of 1,500 people asked, 408 claimed that raising a girl is easier. The question that the researchers want to ascertain an answer to is the national survey wrong? Okay, so we'll have to figure out what that means to be wrong. So to conduct the hypothesis test here, we need to identify the null and the alternate hypothesis. So we need to see where was the population parameter stated. That must be the 24% because it's based on a national survey. So this is going to be a population parameter. So we know that the null hypothesis should be that parameter is equal to 0.24. What is the alternate hypothesis? Well, we're not interested in whether it's less than, is it less than the stated 24% or greater than the stated 24%. We don't care whether it's less than, or we just care whether it's wrong or different. Should it be different? So to be different just means you're not equal to 0.24. Okay, so with that, from the alternate hypothesis, we can tell that this is a two-tailed test because it's not a greater than, it's not a less than, it's a not equals to. So two-tailed test. All right, now what's the claim? The researchers want to know whether the national survey is wrong. So is it wrong? So what are they claiming? They are claiming, yet again, H1. So the claim is it's wrong. We'll see if that's true or not. Okay, so we know who the claim is, and we know what the hypotheses are, and we know we're conducting a two-tailed test. All right, Now we want to check for normality for our sample distribution. So we're going to check NP times 1 minus P and see if that's greater than or equal to 10. Sorry, and we're going to see whether that's greater than or equal to 10. So for us, that is 1500 times 0.24 times 1 minus 0.24. Oops, times 1 minus 0.24. And that's 273.6. Which is definitely greater than or equal to 10. And yet again, we can suppose that the second condition is met. Sorry. Because we're dealing with a national survey versus 1,500. So, we know that 1,500 is definitely less than 5% of the American population. All right. So now we know it's normal. So we're ready to proceed towards the test. We're going to presume the alpha value for our test is 0.05. To conduct the test, we need two values. We need the critical value, which is the Z alpha value, and we need the test statistic, which is the Z of, we'll just call it Z of P hat value. Okay, so where do we get the alpha value? Well, the Z alpha value actually is a misnomer here. So if we have a two-tailed test, then we're not interested in the Z alpha value because it's a two-tailed test. We're actually interested in the Z alpha over 2 value. So we take our alpha level and we divide it in 2, because in a two-tailed test, we have 2 rejection regions. Okay, so schematically, you have a normal distribution, and when a two-tailed test, you have 2 cutoff points. So both of those tails are rejection regions. The green area is the fail to reject region, and this cutoff point will be Z of alpha over 2, and this one will be the negative of that. And again, here we're in Z land. Okay, so let me try to zoom in on that. If it'll let me, there we go. So when we have a two-tailed test, we actually have 2 cutoff points. It suffices to find one because the other one is just the negative of the positive. So how do we find that? Again, we take the inverse norm function. But for the two-tailed test, we're going to figure out what 1 minus alpha over 2 is. So for us, that's inverse norm of 1 minus 0.05 divided by 2. So second vars, inverse norm, 1 minus 0.05 divided by 2. So our cutoff is 1.96. So that's 1.96. So that just means the 2 cutoff points in Z land are 1.96 and negative 1.96. So now all we need to determine is, does this ZP value fall in one of these red areas or the green area? To find the ZP, we do the Z transform. So that's P hat minus P over sigma P hat. So P hat, that comes from the statistics, the sample data up here. So 408 divided by 1500 would be P hat. So let me do a little bubble here. equals 408 over 1500. And that is 0.272. Okay. There we go. All right, so we're finding this test statistic, ZP. So we're going to take 0.272 minus 0.24, which was our P value, over the square root of P times 1 minus P all over 1500, which was N. So what do we get if we compute that test statistic? So 0.272 minus 0.24 in parentheses divided by square root of 0.24 times 1 minus 0.24 divided by 1500 in square root. So we got 2.9. Yeah, 2.9. So I'm going to write that. Try to just put it right in here. 2.9. Okay. So once you have that 2.9, then the question is, does 2.9 fall in the green area or one of the red areas? Well, the cutoffs for the red areas are negative 1.96 and positive 1.96. So the 2.9 falls decidedly over here in the right tail. So that's in the rejection region. So that tells us, based on the comparison between the Z alpha over 2 value and the ZP value, the test statistic versus the critical value, we are going to reject the null hypothesis because the test statistic 2.9 falls within one of the rejection regions. So, how do we state the test? For a two-tailed test, we compare one of two things. We either say one of two things must be true. Either ZP is less than negative Z alpha over 2, or ZP is greater than Z alpha over 2. If either of those are true, then we reject the null hypothesis. If it fails, then we fail to reject, right? So what did we find? We found that 2.9 was definitely greater than 1.9. What was the number? 1.96. Yep. 1.96. So that implies we reject the null hypothesis. Okay. Very nice. So now what? Well, now we form a conclusion. How do we form a conclusion? We use our handy dandy flowchart. Remember, I posted this in the files on Canvas. So again, first question is the claim HO or H1? So you can think of the top branch as the claim is HO, and the bottom one is claim is H1. Our claim for our problem was H1, so we go down this way. Then the question is, do we reject the null hypothesis? The answer was yes. So the answer was yes. So the conclusion is the sample data support the claim that blah, blah, blah. So conclusion, sample data supports the claim that the actual population proportion is different than 0.24. The national survey was wrong. There you go. So that is hypothesis testing for population proportions. I only use one technique because I did not want to confuse you with separate techniques. There are just as good techniques. I may very well cover them once we get through the hypothesis testing stuff, just to give you some more tools in your tool belt. And I will also show you some calculator shortcuts here. But for now, we're just going to leave this as our first introduction to hypothesis testing. And you will get some more practice with this and really see all the variations that you can have for hypothesis testing. You know, you have two-tailed tests and one-tailed tests, and there are different techniques, but again, I don't want to cover them. So we have seen a one-tailed and a two-tailed test. That should get you going and should be enough of an introduction to show you what a hypothesis test actually looks like and what it is required. So there you go.